I'm going to talk about something a little bit different, less different than what I talked about last time, which is interpretability in deep predictive models. So the motivation for this setup is that there are a bunch of successes for AI in health. In the bottom left, we have an example of people detecting prostate cancer from a pathology slide. In the bottom middle, it's diabetic retinopathy detection from a retinal fundus image. To the right, you have early detection of septic shock in the ICU. And in the middle, you have somebody trying to estimate the BMI of a person from their retinal fundus image. But oftentimes when you have these successes, the performance can be surprising. What I mean by surprising is if you told somebody who's like an expert at looking at retinal fundus images, hey, estimate the person's BMI, they're not trained to do it at all. And so they can't really do a good job at it. The estimating BMI is not really like a clinically useful prediction task because you just measure their BMI and not take a picture of the back of their eye and be like, hey, this is their BMI. But the one on the right is actually a useful one where people use the electrocardiogram, which is the electrical measurement in your heart, to estimate the ejection fraction, so how much your left ventricle can squeeze out. Typically, the ejection fraction is measured by an echocardiogram. The echocardiogram requires an expert to collect the echo. Then there's some labeling process, either machine or human on top of that. So being able to do it from an electrocardiogram would be cheaper, easier, and faster. But it was still surprising. Most people, when they think about cardiology, separated the electrical system from the plumbing system. And this is an opportunity for scientific hypothesis generation or just general scientific understanding. But you don't really know what to look for. Right? Because people weren't trained to do the task. They weren't actually doing this up front. Rather, they built some kind of predictive model and they're like, hey, I can predict well. By what basis can you predict well? And for this, you need some form of interpretation. So what is an interpretation? Well, math can always define a concept as far as a model is concerned. And that quantity needs to be translated into somebody's brain to actually mean something. And I'm going to talk about it with really flexible nonlinear models, but the concept is not really different than what you'd see in linear regression. If you had linear regression, you have a bunch of regression coefficients. If I asked one of you, what does that regression coefficient mean? You could maybe tell me that, hey, you might tell me that, hey, if I perturb one of the inputs, the output will change by that. But that's a causal interpretation, requires knowing your confounders, not conditioning on colliders. But still, there's like a very precise mathematical definition. You can write down in closed form what the coefficients are. Okay. Interpretations can also be different for whether you want to interpret a model or you want to figure out what's going on in your data. To first mechanically see the difference, when you have a model, you typically have access to it as like some kind of program that you can evaluate. So here I have a model, which is a conditional distribution of a label given some inputs x, and you'll pass in these inputs x, and then you'll see like what the prediction is. While with data, you don't have access to this actual simulator. You only get to see samples. To think about it a little bit more concretely, imagine in your data, y has mean x1 with it's normally distributed with standard variance of 1. And in your model, you just output 0 everywhere. They need not be tied because your model may not fit your data perfectly. But models are useful in service of building an interpretation. The way that you abstractly think about it, you have some data, you have some model family, you take that model family and the data and figure out the model in the model family that fits your data well. And in this, you get a trained model, and this trained model can be useful in service of understanding what's going on with the data. But the data imposes limits on the model. Concretely, imagine this data generating process. F is like the sampling distribution of data that you observe. Y is a label. X are the features. Here I only have 2 features. And it just happens in my data that the first dimension of the feature is always equal to the second dimension. Then we can ask ourselves, what is the predictor here? The predictor will be related to the conditional distribution of the label given the inputs. And this is only defined when x1 is equal to x2. And you can see that in the equation. You can actually point to it because it's low enough, which is right here, where in the denominator, when x1 is not equal to x2, you're going to divide by 0, so it's not going to be defined. But if you trained a model and you think about it like a piece of code, you can pass in other values. It's just not grounded by the data. A traditional interpretation, like if you opened a statistics book or even a machine learning textbook, would be one of conditional independence. Here, the conditional independence statement says, hey, does the feature j, xj, provide any information about the label y, given knowledge of the rest of the features? You might be like, well, that formalism is good, I can use it, and maybe the problem here is like, I don't know how to use that formalism with nonlinear or flexible models. But there's actually been a ton of work recently in machine learning that's like, hey, we can use deep generative models, we can use deep predictive models to improve the power, to improve like the false discovery rate control. And so it's not exactly what's going on, and it's not why we need something else. To get an idea of why we need something else is that in all these problems, individual features are less defined. What do I mean by that? Like imagine I have a task using chest x-rays on the top left, and I want to predict something about their cardiovascular health, something about a person's cardiovascular health. Say like, I don't know, let's make it very concrete, they're gonna have a heart attack in the next couple of years. And then you might say, a priori, I'd expect the heart to be important for figuring out if they're gonna have a heart attack in the next several years. But then if you ask yourself, is the heart like a fixed position feature in these chest x-rays? The answer is no. Like if somebody is larger, their heart might be shifted down. If somebody's aligned towards the top of the image, their heart might be shifted up. And so like you could ask the hypothesis of, hey, does imaging my heart with the chest x-ray provide any extra information about the label of interest given some basic demographics? But finding the heart in and of itself would be like a heavy machine learning task. At minimum, you'd probably want somebody to create a segmented data set, they'd label it, you'd train something to predict it, and then maybe you could use that in that way. But instead, you could just try to go more directly and try to form like interpretations or highlights of these images that are tailored to the instance itself. It means that they depend on the input itself. And you could do this in like a very straightforward way. If you're familiar with predicting or training deep predictive models or deep neural networks, gradients will appear everywhere. And so one thought you could have is like, hey, let me look at what the gradient is with respect to a fixed label value at my input features x, and you'd get something that is the same size of x, because the gradient is the dimension of the input. But first, it's a local quantity. To interpret what the gradient means, you should have some idea of what the Hessian is. Two, and when you're in a high-dimensional space and you have like a manifold of support in that space, the gradient can actually point off that manifold, and you'll be away from the support of your data, kind of what I talked about earlier when x1 is equal to x2. But they're simple and fast. But if you were to evaluate them in an intuitive way, like, hey, take the maximum gradient values, take the top 10% of it, and see like how well do they predict, they don't really predict that well. So what we'd like is something that is grounded in the data generating process, simple to follow, and we want it to be fast to compute. So one thing we could try for is a subset of the input x, so a subset of the features that retains a lot of the predictability. And this is where the idea of learning to explain comes in. It's described by this picture on top. You have an input x, in this case it's a chest x-ray. The part where you're learning to explain is the middle part where you select a region that depends on the input x. That's the green box. And in the last part, you take that selected region, and that's what you want to say is important, or you'll make a prediction from it. You can write down an objective for it that has two terms. The first term is predict from a selection, where you have the label y, again I can reach it, and you want to predict it from the selected region, which is the green box of the chest x-ray in the top right. And then there's some penalty to encourage simplicity, because if I want to predict as well as possible, I want to see the entire input, and so I want to have some cost of growing my input. And there are a couple of examples of this. The original Learning to Explain is by Chen, Song, Wainwright, and Jordan. And if you were to run this on MNIST, so MNIST is a digit classification task, and you were to sort of run it really well and train it good, you'd get this as the result. The explanations, like the important pixels, are marked in dark red. So this is an example of the important pixel for this image. And this gets 96% accuracy. You should all be like maybe mildly confused or concerned at this point. Probably the thing that should be most concerning, if you look at the 3, you see this pixel all the way to the very right. If I showed that to any person, you'd be like, is this a 3 or not? It's going to be black almost for every image. And so you're like, what's going on? At this point, you should be like, asking this question. So what's going on is that when you actually set up this objective to learn to explain, you want to predict from the selection. You might think that means you should predict from the selected values, so the actual values of the chest X-ray in the highlighted region, but you could actually predict from the selection location itself. And so what do I mean by that? Imagine that you get to see this X, and then if the prediction of X should be I, you just turn on the ith pixel. You're like, that's the one that I want, and you hide everything else. If we look at the two terms in the objective, you'll be able to predict from this selection well, because the ith pixel is only on if the prediction should be I. And it's really, really simple. There's only one pixel that's highlighted. And so this is kind of why you see this result. Putting it another way with dogs and cats, people seem to like dogs and cats. You have the same kind of concept. Here, when you see a dog, what the model will output is any pixel on the left side of the image. When you see a cat, it's any pixel on the right side of the image. Well, the actual prediction model at the end will actually classify, is a pixel on the left, is a pixel on the right, not based on the values of the selected input. And so again, in words, the selector is making the prediction. The selector can transmit a ton of information because it's like a binary code. If you have a megapixel image, it's an amazing amount of information you can transmit. So you don't even need to transmit the labels. You can transmit uncertainty about them that could be read off in the predictor. But kind of like we've defeated ourselves because the classification problem is happening in the selector. Now we need something to explain the selector.
Where's the selector coming from?
The selector is just an input. The selector is this function here on X that's trained to maximize this likelihood.
Okay, so the selector is also trained.
Yeah, the selector is trained, yeah. And so we need something to explain the selector. We kind of don't want to do that, but also the evaluation we had was not detecting what's going on. We're reporting 96% accuracy. There are evaluations in the literature like retraining, where the concept of retraining is you take whatever is highlighted as important, you create a new data set paired with the original labels, you train a model and you say, what is the performance? In this case, such an evaluation would say, hey, the performance is good because it could just read off left, right, left, right, left, right, and the predictions would be good. Retraining is still a good idea because you don't want to evaluate models outside of where they're trained if you're asking questions about the data. And so one thing we could do is just go back to first principles. Instead of saying, hey, we're going to evaluate this train thing together, we'd be like, what would we actually like? So if we had access to the conditional distribution of the label given any subset of the input, so here A is the subset, X is the input, the label is Y, we could evaluate the selection the same way that we would do with a standard model and evaluate the held out log probability. And so that's what this equation is down here. So we take the selection that's produced on X, we pick out the region, and rather than looking at a trained model for it, we ask the actual population distribution, what is the conditional probability? But there's no access to the population distribution. It's at the minimum computationally difficult problem. And so the way that we get access to it is by doing mass prediction. So mass prediction has become popular in all kinds of machine learning, training, even pre-training schemes. But the setup here is relatively simple. Rather than learning to produce the selection, you're like, hey, I want to learn to classify given any subset of the input, where the subsets of the input are randomly chosen with probability 0.5. If you were to solve this optimally, I'm not saying we can, you would recover the population conditional distributions, but it gives you a means by which to evaluate at this point. And we're at least happy now that we can detect some bad selections. So if we pass in these selections and we ask, go ahead, James.
When you do the random masking, are you doing that at the training time or only at the test time for a fixed model that you're trying to explain?
The model can be trained however you want. This is just an evaluator at this point. So it can be done on the same training set, and then there's a held out test set that you'll do this process on. So if you pass it, yeah, go ahead.
Just one question. So the underlying assumption here is that the abnormality is localized, right?
It need not be low. You can sample far apart things. If it's not localized, then you could say oh, the chance of sampling all four things is quite low, and so you might be bad at predicting it. So mathematically you'll be okay, but in practice, yes. Okay, so when you actually try to classify with these pixels, you don't do a good job, which is what you'd expect. You get basically chance, which would be about 10% here. But anytime I give you an evaluator, then if the evaluator can be optimized, I can produce an explanation. And so that's what's happening in this step here. So rather than learning to explain where you train the model and the selector together, you're going to say, hey, take my fixed evaluator that I have that's providing me with the score. Let me optimize over that to find subsets that have high log probability under this evaluator. And you can do this. The optimization problem is a little bit difficult. What makes it difficult is that you're optimizing over a distribution of discrete selections. So you'll use score function gradients and other variance reduction techniques to make the stochastic optimization actually work. And you can actually train them together in that they're two separate objectives, but it's not like you have to finish training one first and then train the next one. You could train them simultaneously. And then if you were to do this on the simple imaging example I had, you would find that, the accuracy on this method called RealX is pretty good. When I look at the selections, I get 86.7 accuracy. You lose something because you're hiding some pixels, but it's better than the other two existing learn to explain approaches. Just to be concrete, we fixed all the optimization choices, replicated all the variance reductions, and made something that is equivalent to RealX, except for whether you learn the evaluator separately or you train them together. That's what BaseX is, and you can see that BaseX's performance is not great. So we performed an evaluation for cardiomegaly. The reason we picked cardiomegaly is because it's relatively well defined to classify. Cardiomegaly is like your heart is relatively big. To understand if your heart is relatively big, you need to have some idea of the size of the chest cavity. You also need to have some idea of the size of the heart. And the regions that were important are highlighted in red for the various methods. And we just asked radiologists to say, how well can you make a prediction on cardiomegaly given what you've seen? Well, for some of these methods, you only ever see some part of the heart that's in the middle, so it's not really possible. But the radiologists who are trying to make the prediction were like, hey, with RealX, it's generally the best one. So the average rank is almost 1. But go ahead.
Explain how exactly was that done? So they see a spot of the image?
Yeah, they see a spot of the image, and then they're like, I want to tell if this is cardiomegaly or not. And can I tell, from these 4 images, which one can I tell the best from?
And then you compare between different approaches. And
Yes.
They know it's blinded to them?
It's blinded, yeah, they don't know. Yeah. But I have this thing that's set up here is evalx. Evalx is kind of difficult in terms of what it's asking for. It's asking for a conditional distribution on all the subsets of the input, so it could be really, really difficult to do. At least computationally, there's a lot of things that you have to represent. And so we tried to play around with this on this task for making MRIs faster to acquire. So the way a magnetic resonance imaging scanner works is that you collect a bunch of frequency space data. Once you have that full frequency space map, you take the inverse Fourier transform, you get the reconstructed image. From that reconstructed image, a person looks at it and is like, hey, there's some abnormality. In this case, it's a knee. Could be a meniscus tear, maybe an ACL sprain, ACL tear. But the idea behind a lot of work, and this is going on for many years in MRI imaging, is that if you can collect less of the case space data, less of the frequency space data, the images are faster to collect, they'll be cheaper to collect, and so there are other things that you might be able to use them for where both speed and cost was a limitation. And so we've decided to think about the simplest algorithm you could possibly imagine to make this faster. So here, the things that you're trying to collect are columns. So the scanner can give you different columns of this case space, and so you want to identify a subset of the columns from which you can make a good prediction on. And we're like, okay, you have this evalx, which is supposedly giving you the conditional distribution on the label, given any subset. So you can think about a very simple algorithm. You take whatever evalx produces, then you take a validation set, you sample a bunch of masks randomly, and you're like, hey, do I have good performance or not? And pick whichever one on the validation set has the best performance. And you can do that, and it works quite well. So there are 5 different methods here, and there are 2 different tasks. So meniscus tears, your meniscus is torn, ACL sprain, also your ACL sprained. And here, the RSS classifier is basically training a model on the full spatial data. So you take the full case-based data, convert it to spatial, then train a deep neural network on it. And it performs at this horizontal line. The reason it's a horizontal line is there's no acceleration for it. There's no way to make that faster because we're assuming access to the full thing. On the x-axis, you see different acceleration factors. An acceleration factor of 20 means you can only see 5% of the case space. An acceleration factor of 8 means you can see 12.5% of the case space. And we see some interesting things. One is that even with only seeing 5%, you can get relatively good performance on these tasks. But for the purpose of what I'm talking about, the ones that we should pay attention to are the center fraction in URC. So the center fraction of the case space is the low frequency information, and a priori that's where you would expect most of the information to classify it to be. And then there's eval x plus the center fraction. We see something surprising that this yellow line is above the green line. And so to putting it in words what's happening, there's one approach where you like cut out the center fraction, train a model, see how well it performs. That would be the green line here. And another one where you take the eval x with the random prediction and you then use the same like fixed input on that model and evaluate it. And we see that when you train with the extra random predictions, your performance is actually better in general. So like eval x, even though it feels like a hard problem, you're getting something from it, and that's because there's regularity. If I have 2 conditional distributions that are very nearby subsets, I can learn from a nearby subset even if I'm not training on it directly. At its core, eval x provides a score for subsets. So if B is like a subset telling you like which pixels or which regions to keep on, the log probability of this evaluator for the fixed label and the selected region will provide some score for that subset. But many explanation methods, like if you open the literature and you see like things like SHAP, can be broken down into 2 steps. One step is like a score for subsets. Another one is a summarization step to take that function on all subsets and summarize it for each individual input. And so we could go ahead and take the same idea we just saw instead of trying to find this subset of high prediction, but we can produce Shapley values with them. So Shapley values satisfy some properties, efficiency, meaning that the sum of the Shapley values is the difference between the full and the empty set. Symmetry, the contributions are the same, the Shapley values are the same. And if inputs that never contribute have Shapley value 0. And we can apply the same idea and we can learn to produce Shapley values. The premise is that like the original Shapley value setup is an optimization problem for each input, and that can be slow to do, especially when you have very large inputs. But here, if you learn a function that produces them, then to actually produce what the Shapley values are, you can do it with a single forward pass of a neural network.
Sorry, can I ask
Yeah, go ahead.
extremely basic?
Sure.
What is the Shapley value or what do you use it for?
A Shapley value in the context of what I'm saying is a highlight of an image. And what I'm going to use it for is I'm going to try to tell you that that highlight of the image is going to be predictive of the label. I'm going to talk about evaluations in the last sort of third of this. And so if you still have that question once I talk about that, then get it for me. One follow-up question you should ask is, if I have this most informative subset, why am I even talking about this? I'll try to answer that one as well, too. Yeah, go ahead.
So one thing about like a couple of the slides ago that you are selecting the mask that to acquire cases. What's the so because that mask is predicted, correct?
Uh-huh.
So what's your input that predict that?
That's a global mask in that case. So we want you don't want a different mask for every input. There, it's like the simplest question possible is like I have to program my machine once, and so I can only have a fixed set of things that I'm acquiring. You could make it input dependent and sort of make it active. So like if you see a column, then you can try to pick a separate column. But this is like the most simple approach. You have like a fixed mask, and you want to figure out like which columns to sample in the case space. And you can produce some nice looking pictures. Like if you do this on ImageNet, here are a bunch of methods. FastShap is the one I just described. Kernel Shap is like the original Shapley value interpretation. They're gradient-based methods here. kind of these pictures look nice. If you look at the FastShap one, probably the one I pick on is the gas pump example, where if you're trying to detect gas pump, FastShap highlights the gas pump, while other methods sometimes highlight the person in the car. If you see a person standing to the back of the car, it's very predictive of somebody pumping gas. Part of the reason could be the actual attribution method, but the other part could be the training, because when you train with these subsets, you create a preference for predictions that are from single subsets, because those subsets appear more often than pairs of them. And you can do this on a medical task as well. This is for right branch bundle block. The reason we picked right branch bundle block again is that we kind of definitionally know what the answer is. The right branch bundle block is when the conductance is slow on the right branch bundle of your heart. If you look at like leads 1 or 2, you can see this like M-shaped curve inside of your electrocardiogram. And we can see that when you look at FastShap, it picks up on that directly. Methods like GradCam will highlight other stuff. Other gradient methods, hard to say what they're doing. RealX gets it, but gets other stuff. Part of the challenge with RealX, again, is that the optimization problem that's set up is difficult. You know, it takes a lot of variance reductions to get it to go, and on very big problems may not even work. And both Lime and Shap produce something that matches where the label would be. But you know, you should ask me, you know, we talked about evaluators earlier, and now I'm showing you pictures. And so you should ask me this question: is it satisfying to only look at pictures? Like, you know, somehow the original problem was, hey, I don't know what to do. And now I'm giving you examples of where I do know what to do, and I'm like, hey, I'm actually matching what I do know. And that's the bare minimum, but for the actual problems you care about, the ones where you don't know and you want to highlight these things to figure out what's going on, you can't rely on this kind of evaluation. So let's get back to evaluating explanations. So why do we need an evaluation? Well, one, if you look at different classes of methods, they have different problems. We saw an example of one for removal-based methods at the beginning, where like the setup sounds really great. Learning to explain, maximize the information between a subset of the input and the label, take that subset, and then you have like your explanation. And gradient-based methods have similar issues where people just sort them gradients by their large values, make a prediction, and they're like, hey, this doesn't predict that well, but you know, there are a lot of unexpected failures here. And second, you know, I just said this, but it's worthwhile to say again, is that human evaluation has its limits. This is an example that we did where we were trying to detect diabetes in people who have no history of diabetes from their electrocardiogram. And here, just the deep neural network trained to do it is relatively accurate, 0.82 AUROC. Well, physicians, and these are like cardiac electrophysiologists, so like hyper-specialized to look at electrocardiograms, can't really do it. It's probably because they're not trained to do it, but that's kind of the point. They don't know what they should be looking for, and so they can't tell you, are these highlights good or not? But putting it in words is like, if your expert performance is worse than your machine's performance, can you check the quality of an interpretation? Sometimes maybe if it's using spurious information, but a lot of times, no. So what makes a good evaluation? This kind of gets to the question to the right here about like, what is sort of the setup and like, what are we after even with a Shapley value? Well, if the use case is well defined, you should just evaluate for that use case. Like if you imagine like what you're gonna do is you're going to make a prediction, show a highlight, have a doctor make a decision, and then see if that decision is good, then you go ahead and be like, let me do a crusted randomized trial of this entire thing, because you can check for compliance, you can check for understanding in that, but it'll tell you like what is the effect of this entire process. But oftentimes you don't know what you're looking for, and so it's hard to get such a concrete evaluation. And the use is exploratory, so there's no like formal fixed objective. So you want to have like a proxy evaluation that is, you know, captures the spirit of what's going on. And the proxy evaluation for a lot of what I'm talking about is informativeness. Like the subset that you see of the input is informative of what the label would be, and that's what you'd hope for when you're looking at this. Like if I see that highlight, that's going to tell me if it's a gas pump. If I see that other highlight, it's going to tell me, if I look at that this person has right branch bundle block. And the method for evaluating informativeness is like exactly what you do in the standard testing setup. The way that you do this is you have some input X, you get an explanation from it. The explanations are just ranks of what's important for each of the input dimensions. Then you say like, okay, if I take the top 1% and then I evaluate how well you can predict from the top 1% against the true labels, you'd be like, okay, if it's higher, it's better. I could take the top 25%. I could take the full image as well too. You could do this in reverse and say like, if I exclude the important features, how much does my prediction power go down? But here I'm just going to talk about it as inclusion. And if I do this evaluation for right branch bundle block, I'm not going to tell you what the methods are here because it's not so important right now. You see something funny. The thing that you see is funny is that the performance is better than when I have fewer features. So if I have like 50% of the features, you can see that many of the colored lines are above the black line. And this should be like a little bit surprising. You know, when you have more inputs, generally you'd expect to do better if your sample size is large enough. So this could be like a fluke. It could just be like hey, here's a fixed sample thing. It could be optimization. Maybe you're better at optimizing for certain subsets than others. Or it could be something else. Here's another example. This is just running a bunch of algorithms on diabetic retinopathy from retinal fundus images. And we see the same kind of thing. This black line is the performance with all the data, and we see a bunch of the colored lines are above the black line, so you're performing better with less data. So it'd be a little bit surprising. And now we went something even further. We're like, what if the labels are completely unrelated? So here we produce random labels, so meaning that the labels are completely independent of the x's. And on the y-axis of the previous plots, we had held out log likelihoods. Here we have AUROCs. And now we can see that many of the methods, now I've named the methods, like whether it's FastShap, Lime, Shap, GradCam, all can do better than chance, and a lot better than chance. And we know for sure, no matter what subset that you see, there's no relationship with the label because the labels are randomly generated. And so this gives you an idea that like there's probably some label leakage going on here.
What does that mean?
Oh, we'll see it in a second. It's a good question. So what does label leakage mean? Well, a lot of these explanation methods input the label to produce the explanation. Well, if we look at the FastShap objective here, there's a y that appears in the value function, and there's also a y that appears in the actual Shapley value output. So meaning that it's inputting some label. Similarly, for a gradient, I'm computing the gradient with respect to a particular label, and so I'm passing a label in. And so these properties of the label can come through in the selections, and then when I try to predict that same label, I've leaked information about it. And many of these methods that I described, almost all of them need a label. You'd be like, is this unwanted? Maybe this kind of leakage is fine. You know, my performance is really good, and so maybe that's what I care about. But you can imagine just like a really concrete example where you observe in like an admission note that the patient denies chest pain. And so that's what the person has written in the admission note. Then 1 year after, just like 1 year after that admission, the patient has a heart attack. And then you ask the question, hey, I want to find a subset of my input that maximizes the probability of this label. Well, you'll just forget about patient denies and you'll just highlight chest pain. Because the probability of having a heart attack if somebody says chest pain is a lot higher than if it says patient denies chest pain. The problem here is that you're kind of hallucinating what's important by hiding parts of the input that contradict with the label that's actually observed. Here, what's happening is there's a bunch of noise in between. We don't see what happens between when the note is written and the actual event, and that noise could have pushed them towards a heart attack or prevented it. And so once we observe that, we can just throw away things that are not related to the label that is actually observed, okay? Rather than paying attention to what's informative. You could say instead, let's use the model prediction, right? So, you know, there we were using the actual label that you observed to produce these highlights. Instead, you could say, let's use the model prediction. The model prediction in this case is going to be the label that maximizes the probability. And it doesn't actually see the actual label, so you can't leak information about the label. But you'll get something that's still unexpected. Like suppose that you had a model that outputted the probability of the maximum class is 0.4. And then what you could do is you could try to find a subset of the input where the probability of the actual class is much bigger than 0.4. So rather than like removing what's important for removing what contradicts for the actual label you see, you can remove what contradicts for the predicted label. And that's here you see that the probability is much smaller than 1, and so there is information in your input that's contradicting what the label actually is. Again, you're hiding information against the predicted label. And so now we're going to try to go for an alternative. Like we want to try to come up with something that doesn't need a predicted label or doesn't need the actual label in and of itself. And so we define things distributionally. So here, there's a value function at the top which scores different subsets of the input. It's the negative KL divergence between the distribution where you get to see all of the inputs and then the distribution of the label given subsets of the input. Once you have this like subset scoring function, you can summarize it in different ways. You can produce a Shapley value for it. So the next two equations are the fixed Shapley value and then learning to produce a Shapley value. All the same ideas we saw before port over to this distributional value function. And here I'm going to show you like a whole lot of methods just so we learn a few lessons at the end of it. So we're going to look at model agnostic methods like FastShap, RealX, We'll look at popular methods for images like GradCam, integrated gradients. We'll also do a version of SHAP that doesn't evaluate models outside of where they're trained, and we'll see the KL versions that we just introduced. And if you look at this, you now have pictures where you don't cross the black line, and so it's a little bit helpful. You don't cross them severely. And kind of like a good curve here is one that's like up and towards the left, meaning that if you look at the most important selections, you'll have the highest likelihood for what the label is. And we can see that some methods perform a lot better than the others. If we look at FastShap KL, if we look at SHAP KL, RealX, they all do relatively well. So does GradCam, it's hidden behind here. But then I'm going to show you results for two different problems. The one on the left is diabetic retinopathy. This is the classification from the retinal fundus images we saw. On the right is 30-day readmission prediction from clinical notes. And we can see one thing that you should take away is that you can cross the black line again. The code here is set up that you don't see the label, so you can't selectively read the label, hide information that contradicts the label, and improve your predictive performance. So what you're seeing is actually something that's related to optimization, meaning that like if you could see the actual predictive model on the full data set, you're doing a little bit better on less. It also could be related to the feature dimensionality. But the important real takeaway is that the ordering of the methods also is going to be different. When I look at the left, and now I'm going to tell you that IntGrad and FastShap KL and SHAP KL do pretty well. If I look at the right, IntGrad doesn't perform well. If I look at the left, GradCam is now terrible. But the real takeaway from this is that from actually looking at predictive evaluations, you can see there's quite a difference between all these methods. Yeah. And now I'm just going to tell you some brief takeaways. Yeah, go ahead.
Quick question on the last slide. So
Yeah.
If a subset of your features are knowing your spurious correlation, let's say if your retinopathy image, there's some pencil markings, then would you expect that not including those features would give the model better prediction? You would expect that drop off, right?
It depends if so if my model, if the full size model is using those spurious correlations, that's true. And so that's what I would call as estimation error. Because the full size model has the input, it's just taking the shortcut rather than using what is actually more predictive in the input.
Right.
Yeah.
Exactly. So in that
Yeah.
case, then having this downward trend at the end is not necessarily a bad thing for the evaluation method.
Yeah, it's not necessarily bad up at this point. Like before it was bad because you're actually using the label and you're just copying out what's in the label. At this point, it's not actually bad. I would agree with that. Yeah, that's right. But things where you're quite far away may not be good. Like if you're looking at GradCam, it's not very predictable of the label. Yeah. So there are a lot of takeaways here, and I've just summarized them quickly. One is that if you use really popular methods like SHAP is in Amazon SageMaker or Lime, they can leak the label. And what that means is that if you were to actually run them in the way that you set up the conditional distribution with the label that you observe, you will hide things that are against what that label is. You can do it with a distributional approach, and then you don't have that problem anymore. But you also have to be careful about these methods evaluating models outside of where they're trained. If you feed in a mask token to a model and you're hey, should it do something good? It's actually undefined what it will do. And the lesson at the end is you have to evaluate. No matter what method you choose, Here, there's some methods that I introduced, RealX, ShapKale, or FastShapKale. They all don't take in the label, and so you could use them and evaluate them. But without an evaluation, you shouldn't do anything. Like if somebody just shows you a picture and they're like, hey, this is what's going on, you should ask them, like, how does that relate to my data? Like, what sort of held out data did I use? How did I check it? What is the performance on that held out data? But there's like a ton still left to do. Like this sort of took us from a place where like you look at these highlights and these highlights actually aren't related to the label in the way that you expect them. Now that we have some highlights that relate to predictability, but they don't actually take you all the way there. Like, you might want like continuous things inside of an ECG. You might want to relate to like the tabular features that are inside of an ECG. And so this is sort of like the first most basic question you could get to. And there are things that are like specific to domains that would make it more useful. And I'll take any questions if there are any remaining ones.